Okay, so last Monday we looked at sequential data and sequence models, basically models that are able to learn and predict data that comes in a sequence, right? Where the sequence matters, the order of the data matters. And of course, we know that this is really key for time series data and for language data, basically words in a sentence and so on. And we looked at the different kinds of models. We looked at, there are three, there are more than this, by the way, but we looked at the ones that really mattered. We looked at the basic one, which is the recurrent neural network, the RNN, which is effectively just a single feed-forward layer where the output is circled back and fed back into the input and added to the input through a set of weights. So basically, we take the output from a regular linear layer, right? Pass it through take the output from that linear layer and we put it back into um, the the input and sum it to the input, right? So the output is always going to be the weighted sum of the actual input at a particular point in time plus the previous output, right? Also weighted, the weighted sum of the previous output. And all of that, of course, is passed through a hyperbolic than activation function. And that gives us what we call the hidden state. So the hidden state becomes a kind of memory, a way of retaining information about the past state of that model. Because this this formulation, right, where you take the output at a previous time step and you add it back is kind of what leads to what we call a moving average, right? And a moving average basically keeps track of, it kind of has a memory of what happened in the past. So this introduces memory, right? But it is a very rudimentary kind of memory, which yes, can do a few things, but cannot do much, right? So can use it to predict the next in a sequence. So this wasn't very good. It had a bunch of issues, including vanishing gradients, exploding gradients, and so on. And so researchers continue to improve on it through different other steps. That there were different other models and iterations. I just didn't bother going through all of them. You can go do some more research. But the LSTM was one of the most prominent ones that solved the problem of vanishing gradients and exploding gradients by introducing what we call gates, right? Introduced a gate, input gate, and output gate. So gates are basically ways to control how much or which aspects of the historical data comes back in, right? So the forget gate determines how much of the historical data comes back into the current state, while the input gate determines how much of the current data, that you are trying to predict, how much of it comes the into the state. And then the output gate determines how much or which of the internal state goes out as output. And that output is what is then channeled back into the input, right? In that feedback loop. While the internal state we was maintained something called a cell state. And that's basically LSTM, right? You have a cell state, which is just re representing an internal state. And then the forget gate is to determine how much of that cell state, is allowed to affect the next cell state, while the input gate is used to determine how much of the actual input from the current state or from the current input for current X or time step is used to affect the state, the internal state. And that internal state is what is used to calculate the hyperbolic pan and everything. And then the output is calculated, right, based on the activation function. And then the amount of the output that is allowed to go out, is determined by the output gate. So the whole concept of gates were introduced. That's the most important thing to pick from that. And the reason why it was able to solve vanishing gradients was that it changed it from being a product of the weights to being a sum of the weights. The gating mechanism and the way the cell state was reorganized, it meant that the primary factor was was a summation rather than a product. The gates eliminated vanishing gradients. So this is kind of a summary of it. And we can go into all the maths, but I'd rather do a bit of coding now. Yeah. So basically it uses addition, right? Instead of multiplying repeatedly, it uses addition. Essentially, the the forget gate, right, determines a measure. So instead of using weights, basically they were using gates. So the forget gate determines how much of the previous cell state comes in, while the input gate determines how much of the current input comes in. And those two are summed to form the current cell state, which is CT. And then the current cell state is passed through the activation function and then passed through the output gate. So the output gate determines how much of the cell state comes as an output. And so they were able to adjust the relationship from being a weight to being a sum. The gates are implemented using a sigmoid function. So remember, the sigmoid function always gives you either zeros or ones. So it will either totally eliminate something or totally boost it. All right, either allowing it to pass if it is a one or blocking it completely if it is a zero. So that is why they are called gates. And that's simply how they solved it. So, and then we had the GRU, the gated recurrent unit, which was a simplification based on understanding of how LSTMs work. But the fact that LSTMs are a bit slow because of so many gates, so much computation. So researchers came up with a GRU, which they reduced the number of gates just to the upgate gate and the reset gate. And there was no separate cell state. So it still used this same hidden state, which the RNN used before, but with gating mechanism instead of um, instead of um, a weight multiplication mechanism. So yeah, we are going to look at this in practice now. The RNN, the LSTM, and the GRU. So I'm going to start off with a simple demo, right, of these three different types of models, predicting data from a sine, um, basically a sine wave, right? So let me show you how that, and then after that, we are going to look at how we can use this to predict, right, the next item. So remember, we use this to predict the next item that comes out. That is what it always does, right? You look at a list of things, and then based on that sequence, that's why it's a sequence model, we will predict the next, what it should be. And that is how the whole concept of generative AI, is achieved. Basically, predict what should come next based on the sequence that we have been trained on. So I'm going to just place this here first, just to help us. All right. So if you look at this, yes, this is how it looks like. So at every point in time, this X is actually a sequence. And that sequence of information, you are going to feed it in one at a time, one at a time. And then you ask it to predict. For each time you feed in like X, you want it to predict the L. So the L is is a prediction of what what's the next X that will come after this current one, right? So when you are training it, okay, you are going to give it X, all the X's, and then you are going to give it all the L's. So what that means effectively, let me explain that now, is you are going to use the same data as the input and also the true values to predict. So let's assume, yes, you have this simple X of 1, 2, 3, 4, 5. What it means is that the Y that you use to train this model should be the next in the sequence. Okay. So let's say that will be 2, 3, 4, 5. Okay. Right. So let's start with here we're basically trying to use this a sine wave and all of that. But I want to explain this. So if your X is 1, 2, 3, 4, 5, then the Y is 2, 3, 4, 5. So the question is, the 5 is where we're saying, okay, when we are at 5, you should be able to predict. So the training data is actually going to be from 1 to 4, the X, while the Y should be from 1 to 5. Okay. This is typically how it is because what we are saying is, um, so let's see, original data. The original data is actually 1, 2, 3, 4, 5. So that's the sequence. So what we are saying is that when I have 1, I want you to predict 2. When I have 1 and 2, I want you to predict 3. When I have 1, 2, and 3, I want you to predict 4. And when I have 1, 2, 3, and 4, I want you to predict 5. Okay. So that's why the X data is this. So it's going to be sent in sequence, and this Y should be what it should be predicting. That's really what it is. All right. So if you are training a model, right, this is how you train it. Um, you see that you do a prediction based on X, right? And then the loss uh based on Y, right? We're going to, this is a standard training set, but you are going to see how um we generate the data that we use to train it, right? When we are talking about the X and the Y. So we're going to see that when we are generating. Okay. So I'm going to, let's just go through this. But this is just an explanation of how that sequential generation is happening. Okay, so um let's go ahead, right? So the first thing is I don't need, if you don't have touch, you can install dependencies, but I have this already, so I'm not going to bother running it. So we will need to import touch.nn as usual, and then numpy so that we can do plotting. We can pull the touch tensors and manipulate them so that we can plot it. Then we use a matplotlib. Then the touch.manual seed is to allow whenever you're generating random numbers, it always starts in the same with the same seed. So that will help us to ensure that um these tests, the tests that we have here are repeatable. Okay. So the first thing we'll do is the objective of the experiment is to try to train a model to predict the next value of a noisy sine wave. Okay. We actually did this with a you know a network, a standard feed forward dense fully connected network, right? But here we now have this as remember it's a time series data. So we will now try to train it with time series data. So the reason why we are picking the data set is generated is a sine wave basically, but it has some noise introduced into it. Okay, it's inherently sequential. It requires memory because it is inherently sequential. It's also visually intuitive. It's easy for us to see the data visually. Okay. And then it also exposes the weaknesses of a recurrent neural network. So that will help us to see where LSTMs become better. So the idea is of this experiment is that we are going to generate 50 time steps of time series data. So we're going to generate a sequence length of 50, right? And we're going to generate 1,000 sequences. So we're going to generate sign data that has sequence length of 50 and 1,000 sequences. And then we'll train a model. So the model will be trained so that it should be able to predict the 51st value because that's basically what a series recurrent neural network predicts. It predicts the next data based on training you have already given to it. Okay. It tries to predict the next value in that sequence correctly. So, um, so this is how we generate the data. We'll have the X and the Y, right? Empty, we start with empty list. And then we will just use a lint space. So remember, a lint space is a function that allows us to between two values, the start and the end value, will generate any given number of values that are equally distributed in that range. That's what lint space is. Linear space, basically. It spaces the values linearly in a range. So here we use mp.pi, which if you remember, since we are talking about a sine wave, right? Pi is 90 degrees, right? Um, sorry, pi is 180 degrees. So 2 pi is 360 degrees. Pi over 2 is 90 degrees. So for us to do a full sine wave, we are going to go across the full 360 degrees. That will give us a single sine wave of the shape of a sine wave, right? And we know what a sine wave looks like. So it starts from zero. At 180 degrees, it goes back to zero. At 360 degrees, it goes back to zero. But at 90 degrees, it goes to 1. And at 270 degrees, it goes to -1. So the range it should start from 0 to 2 pi, which is 360. But here you can see that we decided to make the starting point to be a bit random. So we're not starting exactly at 0. We're starting at a random point between 0 and 2 pi. So we're actually starting at a random point between 0 and 360 degrees on that range. Okay. And then the number of steps, the steps is the actual specific values that we are generating. And we are starting from that starting point, which is a random point between 0 and 360 degrees, right? Which is 2 pi. And we are ending at start plus 3 times pi, right? So we are starting from any random point and we are going to 3 times of pi, which 3 times of pi is 360 degrees plus another 180 degrees. So what that means is that we are going to go a, a full 360 plus 180, which is 540. So we'll go all the way to 540 degrees. So we'll have steps in that range. And so we just calculate the data by basically calculating the sign of each point. But we also add a little bit of random noise, right? In the normal distribution. That random noise, the scale is zero 0.1, so that's the maximum value of the noise. It's always going to be plus or minus 0.1 maximum, but it could be less than 0.1, so 0.95 and so on. And the size is the the breadth of the normal distribution curve. So what this basically does is it generates a sine wave, right? But adds a little bit of noise. So it's not going to be a perfect sine wave, right? And then, um, yes, so we generate this, and then you can see that for the x, right, we take the everything in the sine wave except the last one, and then for the y, we take just the last one. So effectively, a data set. So let me correct it because I think I was thinking of sequence to sequence models here, but this is not a sequence to sequence or encoder decoder. Rather, this is something like saying, um, this is how that, let me just give you how that is generated. It means that if x is 1, 2, 3, 4, then y should be 5. What we are saying is that when I have 1, 2, 3, 4, then y should be 5, right? If on the other hand, x is 1, comma 2, right? Then the y should be what? 3. So we are saying the y is always the next value that should be in that list that should be predicted, while the x is the previous list. So this is how you generate the training data that you would use. This is how you generate training data. Now, the only difference here between here and what we have done is that here the size of the sequence is not fixed. Here we had a sequence of 4, right? And we're predicting that y should be 5. Of course, that's the y, what it should be, what you want to train the model to predict. So if we were to go the full way, right, of generating the x's and the y's, um, this is how it would look like. It will be when x is only 1, then y should be 2. I want to predict y 2 when x is only 1. When x is 1 and 2, y should be 3. When x is 1, 2, 3, y should be 4. When x is 1, 2, 3, 4, then y should be 5. I think. So this is the training data you will actually use to train a model to predict this sequence here, right? So that's just to show you. Um, Now, because you're actually generating a whole stack of things here, right? So to train a model on this sequence, you would have to generate this. So I would actually be generating a three-dimensional stuff, right? So X would actually be a three-dimensional thing, np dot array, right? Um, you could all even say and then you would stack these. But the difficulty we are having with this is that you can only use fixed length, you know, data. So you have to pad and all of that. So I'm not going to go into all of this, right? Because that's a bit it's going to take us a bit away from what we are doing. But I just wanted to show you this is how it would look like, right? This should actually be x0, something like x0, right? While y0 and so on, because you have a number of x's and a number of y's. That's really what it should be. Okay, right. And yeah, well, you could do this and then use a numpy array to just generate it. All right. In which case you could say x is a list and y is also a list. So this allows you to set up that. Okay. So you can see you have multiple x's, 1, 2, 3, 4 x's and also 4 y's. And oh, sorry, this should be x1, x2, x3. While this is y1, y2, y3. Technically, it is more accurate to do x dot append, in the context of since I'm using lists, right? That this would be the correct thing to do, right? So this is how I would generate it, right? That's technically the correct thing to do. All right. But what this loop does is basically the same thing. So you have X, which is a list, and you also have Y, which is a list. Okay. So, except that in my own example that I showed here, you have the X values are variable length, which is a different problem that we will have to solve. But here, link space generates the same length, but because the starting point is, remember, it's a sine wave, right? So the starting point is random, right? Random between 0 and 360. So we can always ensure that we are generating the same length, the same number of items, right? And then the last item, so this the X, you use X, the all the items up to the last but one is used for X, and then only the last item is used for Y. Okay. And that's it. So we generate this list of X and Y, and then we convert them to tensors. Okay. So you now have them as touch tensors. And we could actually, like, when you run this, you will see that this is the size. I could actually plot this. So here it is plotting a single item in the sequence, right? But we say there are 1,000 sequences. We could actually print all the sequences. In other words, there are 1,000 different, think of it like a sentence, each sentence has a sequence length of 50. So you have sentences that are 50 words in length, okay? Or 50 characters, depending on how you want to look at it, 50 tokens. Sentences are 50 tokens in length, and there are 1,000 sentences. That is your training data, right? That's the X. And then the Y would be the next word in each of those sentences, right? So that is, if you were to plot it in a graph, here we are plotting just the first one, right? We are plotting just the first one, but we could equally decide to plot a bunch of them, right? Instead of plotting the first one, I could plot a few, right? Um, let's just say for I in range. Let's say I want to plot the first five. Okay, so I'm not just plotting only the firsts, but let's say I plot the first five. Okay, so squeeze is so you can see, yeah, so these are the five sequences. So you can see they're basically sine waves with different degrees of noise, right? And shifted, you know, phase shifted because the starting point for each of them is random, right? Between 0 and 360 degrees, which is 2 pi. Okay. So this is it. So the 50 of them, I can see how it looks like, right? Um, there are 1,000 of this. I could actually print all 1,000. If we wanted to, it will look crazy and it take a lot of time. But yeah, this is all 1,000 of them, basically. Right, but that doesn't make it's not very useful, at least in that manner. Okay, so that's the data, right? So you can see that this data is sequential data, They don't all start from the same point, right? They don't all start from the same point, but they still follow the same sinusoidal wave. So effectively, if you are training a model to predict this, a model should be able to predict the next one and it should follow a sine wave, um, formation kind of. So this is data that I want you to train. So we start by, in order to be able to compare, see how well recurrent neural networks do in this kind of problem, we start with a model architecture that doesn't know anything about time series, doesn't have memory of the past, which is a basic feed-forward network, a flat network. So you can see that here, what the network we did was NN dot sequential, right, which is three layers or two layers rather, a single linear layer with a ReLU, and then another linear layer with no activation function on the output. Okay. Of course, the number of inputs are 50 to match the number of data points that we are training on, right? There are 10 data points and 50 features rather. So the number of features we are training on, the 50 features are the 50 items in each sequence, in the sequence deck, and then 1000 is the number of data points, which is the number of sequences. Okay, so a simple one, right? The forward, this standard normal forward, we take X, we have to flatten it out first because you can see that the shape of X is actually 1051, right? But it's if what will be sent, maybe the entire batch can be sent for you to train on, right? When you do squeeze, you are essentially converting it to a two-dimensional shape, right? Instead of three-dimensional shape. So yeah, so this defines it. Let me show you what squeeze does. Okay, we could take the X, right, which is what's going to come in, and squeeze it. Okay, so first of all, this is X. Let's just look at the shape of X, right, without squeezing it. It's 1051. But when you squeeze it, um, -1 is the dimension in which you squeeze. You can see it's 1050. The third dimension, 1, is lost. Basically, it is flattening it on the last dimension. So the -1 is telling you which dimension you are squeezing, you are flattening. And that's a -1. -1 always means the last in the list. So you are squeezing the last dimension, which is the dimension at there are three dimensions initially. You can see there were three, right? 1050 and 1, right? We're squeezing this last one, so we get 1050. Okay. If it was 1050 and 2, then we'll squeeze it to 1100, basically. So that's what squeezing does. So it essentially makes it into a flat thing, but it's still batches. You cannot squeeze the entire thing because each batch is a separate training data. Okay, so we've defined our basic feedforward model, right? Now we define our training model, right, which we'll use for all of them. So this standard training model, sorry, it's training function or training loop. We use Adam optimizer. We use mean square error loss because this is not a classification problem. This is a prediction problem. It's a regression problem. We're trying to predict the next in a list, right? And that next has to be a number. It's not a probability. It's not whether it is 0 or 1, right? Or whether it is white or black. But you're trying to predict what is the next number in this sequence. So that's why you have to use MSE loss, which is what you normally use for a regression problem. So we use that loss function. We use this optimizer. Okay. We set learning rate at 0.03, which is pretty low. For Adam, 0.03 is a good learning rate. If you go to 0.1 or 0.3, it's too high. So for Adam, this is a good learning rate. Then of course, this is where we track our losses. Okay. Then we run the training loop. Of course, the standard sequence of actions in a training loop. First of all, predict. So you run the X value through the model, right? And you get a prediction. Then the next step, of course, calculate the loss, which you call the loss function. You pass in the prediction, and the true values. Okay, that gives you a loss. Then you go to optimizer to do the back propagation. So to do back propagation, you need to zero all existing gradients. So you use a zero grad to basically zero any previous gradients that have been calculated. Remember, this is a loop. So there will always be a previous gradient, except the first time. It's only the first time there won't be a previous gradient. But after that, there will be previous gradients. So after that, you now do the backward pass, the back propagation, loss dot backward. And then this will calculate new gradients based on the gradient functions and of course your architecture. And then after that, you do the optimizer.step. Remember, optimizer.step is where your parameters actually get updated based on the gradients that were calculated. So you do that. So you have trained your model for a single epoch based on all this data. And then you pull the actual value of the loss and you append it to the list of losses so that you can plot it. And then, of course, we do this every once in a while. You plot your loss values. It's not all the time. So this modulate thing is to say, okay, every time, every 5 epochs, you print. That's to prevent the thing from overdoing it. So yeah, we use 20 epochs by default here. We return the losses, and it is these losses that are returned that will print. So with our training function in place, we can reuse this training function. So we create a feed-forward model. This is a basic feed-forward model like we saw already. And we train it. Okay. And after training it, 20 epochs, so you can see the loss goes to 0.03 after 15 epochs. Let's also print the last one here, or epoch equals epochs. So we should also print during the last epoch as well. So yeah, let's do this. New model, so you can see, hang on. Oh yeah, okay. The penultimate one. It won't get up to epochs because range epochs doesn't include epochs, so it has to be the penultimate one. So we just want to print the final loss before it goes out. So yeah, so you see it gets to 0.02. And it's not very good performance. If I wanted to calculate accuracy based on this, right? Remember accuracy, you could also calculate accuracy. Um, so to calculate accuracy, we would um yeah, to calculate accuracy, we would first of all do a prediction, then sum, do the sum of the predictions. All right. Okay. Um, yeah, we'll have a little technical challenge. Okay. So I'm going to put in a little bit of code here to help us calculate the accuracy. And then it's just a way for us to, check and measure and see how well this is going. So let me add a function to calculate accuracy. Yeah, so we'll pass in the model and accuracy on the trained data actually. So I'm not going to try to do anything very fancy. We're not doing test train split here. Um, so to calculate the accuracy, you will put the model in eval mode and then you just do prediction. right? Um, and then once we do that, right, we run the predictions, okay? Then we can calculate accuracy by calculating how far away. We can use the mean square. Um, Accuracy, you can basically calculate error away from the prediction, right? And divide by 100. So that's how you do accuracy. So yeah, okay. So we're getting the absolute value of the error. Uh, Predictions kind of line. Well, this is not entirely correct though. Um, this is still error. Okay. So yeah, well we can then plot the loss. So we have this, we can plot the loss. And you see how the loss goes down, it jumps around a bit. This is due to the momentum in the Adam optimizer, right? Um, the minimum loss is 0.0298. So that's okay. But let's now plot this prediction. Let's plot the let's plot this, right? Let's plot the how it predicts. Maybe we'll just take a basic sequence and see if it is able to predict. Okay. Or we'll do that at the end, right? Let's do that at the end. Okay, so this is for a feed-forward network. It doesn't have any idea of memory. The maximum the after 15 epochs, we get a loss of 0.0298. Now, let's see what we can achieve using a recurrent neural network. So if you look at this now, we have this a new RNN, right? And we specify the input size. So in this case, the interesting thing is when we're doing a feed-forward network, we have to make inputs to match the sequence length, right? Essentially, we're considering the inputs, each item in the sequence as a feature, right? That's how you would do it. Basically, you are mapping, you have 50 data points here, right? I probably should have plotted this as a scatter, okay? Um, or let's not let's make it let's make it let's make it a instead of yeah let's make it instead of this, right? You plot it as data points. So this makes it easier for you to see how it is. So predicting the next in the list. Okay, right. Um if I take out this and just we just print only one. Okay, so this is how it looks, right? Single one. All right. So, So th- there are 50 data points here, right? 50 points in the sequence. For a feed-forward network, we would now have to look at each of these as a feature, right? So that's why we have 50 inputs. So based on this, essentially the order doesn't matter. We're just saying, oh, each of this is an input, maybe a feature, and predict the outcome. This is not very helpful. It is not going to be very helpful at all. As a matter of fact, you could try to plot what it predicts when you give, but like I said, I'll do that at the end. Okay. Now, for the a simple recurrent neural network, right? The input size is just one because it's already a sequence, so it knows it is a sequence. The sequence length is 50, but it doesn't really matter. It's going to run through the entire all of each of them in the sequence and use that to learn. The hidden size is 32. This hidden size is arbitrary. You can just pick any size you like. The more complex problem it is, the bigger your hidden size. Okay. Then batch first is saying that in the way our data is organized, the batch is the first dimension. And that is correct because if you look at the shape here, right, we have 1000 sequences, right? Each of sequence length 50. So the batch is the number of sequences, or basically a batch is always a number of training data that you're using to train. And there are thousands of them here. So, and it is a first in this dimension, basically the arrangement of the data or the shape of data is a first. So that's why batch first is true, right? There are certain data that are arranged in a different way where the first dimension is not the batch size, right? Or the number of batches, okay? Or the number of items in the batch. So that's where that matters. But in most cases, of course, batch first would always likely be true these days. So anyway, this is a recurrent neural network. So it's going to give you, it has a hidden size of 32. It's going to give you 32 different outputs, okay? Then that 32 different outputs, we can then combine it using a standard feed-forward linear layer. So see, the interesting thing is that using only a linear layer on the output is not a good idea. Like here, well, here we had two linear layers. So we had a linear layer with a hidden size of 128 and then an output size of 1 to predict the outcome. So you can see that this second layer, the output layer still is retained, right? It is still retained in our RNN. We still retain it, right? Of course, the number of input has to match the hidden size here, just like the other one had to match the number of hidden layers. Okay, and that's it. So when we now want to do the forward pass, right, we'll run the recurrent neural network and pass in the X data. Remember what we said, because the recurrent neural network has multiple input states, the output will contain those multiple input states. The first one is the actual output that comes out, while the second is the hidden state. But the prediction is not going to be based on the output states, right? Rather, it will be based on the hidden state. So we take the hidden state and we take the last one, okay? And we use that to calculate or to pass it into the um this, right? Now there's something I would like us to kind of let's pull this out, right? And let's observe what is actually happening inside a recurrent neural network so that we understand why this is this way. Okay, so I'm going to create an RNN just outside of this, just a standalone single RNN layer. Um, right, single RNN layer, okay? Just for us to be able to, so I create a single RNN layer, then um, yeah, so I just execute the output. Output equals RNN. So I want to just print out so that you see what out looks like. So you see that it is a tensor, right? Out gives, it's actually a tuple that gives you two tensors. So this is the first tensor, and then this is the second tensor. Now let's break it down and see what is in these two tensors. Let's see what's in the two tensors. So since it's a tuple, right, you could say out and hidden. Okay, so let's do that. So we now out the shape, okay, and hidden the shape. So I want us to see what it looks like now. So the output that comes from an RNN, remember the inputs, just for comparison, let's also add X dot shape here so that we can see the tree. So the input is X. So you can see there are 1,000 data samples, sequence length of 50, and just a one dimension, the third dimension. So sequence length of 50. Each sequence, each element in the sequence only has a dimension of 1. So it's not an embedding, it's just a single value, right? Now you put it, so the input size is 1. That's the main thing here. Input size. So in an RNN, what you're looking at is not the sequence length, right? But the input size, which is 1. And then we say hidden size is 32. So this 1 is going to be expanded into 32. So the output you will get from an RNN is going to have the same shape, right? But the third dimension or the last dimension will now have this hidden size. So you've basically generated a new sequence, 1,000 batches, sequence length of 50, but each element in the sequence now has 32, basically a vector of 32 elements in it, okay? So that's what I wanted us to see what this out is. But that is the output, right? But the hidden state, which is the hidden state that comes out from this RNN, you can see what it looks like. It doesn't have a batch dimension, right? It's one single hidden state. But that single hidden state, for the one, it has 1,000, right? For each of the batches, it will have a the same dimension as a hidden size, right? So what we are saying is that this gives us a single 32 um, a vector of 32 elements for each data set or each data point, right? Each sequence. So each sequence gives you this, right? And that is a hidden state. So we will now take this. That's why we are taking this, because in doing this, what we are actually getting from the hidden state is the meaning of the entire sequence. You see that the 50 is not here anymore, right? It has been basically compressed. The 50 different time steps in the sequence has been compressed into a single state that has a single meaning, right? But that meaning is represented by this feature. So essentially, the RNN is taking the 50 and converting it into a single, for each of the 1,000, right? The 50 steps, it gives you a single output, but has 32 features. Think of it that way. It has 32 features that have different meanings, okay? And then these 32 features are then plugged into this linear layer, right? Which will take in these 32 features and give you a single output, right? So that's why you find that it is the hidden state we normally take, not the output. This output, we would take it if we needed what we call a sequence-to-sequence model, because this is still giving us another sequence, right? With additional meaning. But it's not the sequence that we want, but rather the meaning of each sequence. In other words, what the LSTM, or sorry, what the RNN in this case has learned, from that sequence, right? So what we are actually taking is a hidden, which is this, right? And then we take that hidden and we pass it into the fully connected layer. And you see that what we are taking is hidden minus one, which is the last part of it, right? Um, hidden is a list itself, right? And we're taking the last bit of it and we're passing it in. Even though I would expect hidden um, minus one should actually give me just the last, um, but I should have 1,000 of them, right? So that's what this does. So if we look at that, this was just explanatory, right? It's not really the thing. But let me take it out. Um, so if we do a forward, let's now do a forward with that knowledge. Let's do a forward and let's just say out equals um yeah, let's do a simple RNN, right? Right. So you find that we now have an output 1,000 because there are 1,000 in hidden and one because the 32 will be kind of folded into one. You have a linear layer that will take this 32 and based on the training, it will give a single prediction based on the 32 features. So effectively, the RNN is taking the sequence of 30 time steps, generating a feature map that has 32 features, and those 32 features go into the linear layer, and we get a single prediction for it. So that is that. So we will now run this model, right? And after 19 epochs, you see that our loss is 0.037. It's actually worse than this, right? Um, here we had 0.0116. I think I may have to rerun this, but yeah. Um, okay. Yeah, let's see. Okay. So simple RNN, we train the RNN against that train, we still end up with you. If you notice the first time it kind of the loss increased. Okay, so now let's compare the losses. So the feed forward gives us better losses, interestingly, at the beginning. The RNN is jumping around. The RNN um is converging more naturally, right? So now let's try with already it looks like they're kind of almost the same, even though I'm quite interested to figure out why we had um the fit for doing better than RNN. Let me put in more epochs. Okay, so let's put in maybe 50 epochs, and then we start again. New set of data, print the new set of data, feed forward. I'm not even surprised that feed forward is doing so well here because um, you could actually have a feed forward network that does well on recurrent data without being aware that it is recurrent data. So with 50 epochs, we get 0.013. Loss curve, it flattens out. Simple RNN, all right. It could also be that um, we have more parameters, right? The simple RNN has more parameters. Sorry, the feed forward layer has more parameters. So it will do better. It simply has more parameters. So this is where you now see when we talk about Sometimes the architecture matters, but the number of parameters actually matters more than the architecture, right? And this is a very good example. The data is not complex enough. All right. Now let's go to data that has a longer sequence length. Okay. So this has a longer sequence length, 120. We're using a sequence length of um 50 before. Now we have a longer sequence length, right? And again, the reason why the feed-forward network is able to predict better is it is a kind of simple relationship. It is um it is a sine wave, so I'm not surprised. So we start with a simple RNN with a long sequence length. Um, yeah, let's also do the same for the feed forward and train it as well on this new data that has a longer sequence length. Okay. Oh yeah. So feed forward, we had coded the sequence length into it, so I need to modify that. So let's see, length, sequence length. So instead of hard coding this, we will do sequence length. Yeah. Could start off with 50. Oh, well, let's make it a required thing. Right. So, yeah, here was sequence length was 50. Okay. Now we will do this with sequence length of 120. Okay. Right. So Fit4 still outperforms our RNN, which is interesting. Um, Now let's plot them again, so we can still plot again. Yeah, so kind of okay. Um, but we find that the feed forward um tends to fluctuate, probably overfitting. All right, so now let's try LSTM. So with LSTM, same thing as the sequence model, the RNN, but we use LSTM instead of RNN. So we train as well on the long. So one thing you notice, you see that the LSTM is taking longer to train because it has more parameters. Okay. Um, okay. We now plot the LSTM against the RNN. So the LSTM gets better than the RNN. It takes longer to train, right? Uh, it takes longer to get to the same point, but it actually goes below it. So effectively, it can reach more. If I actually increase the sequence length, you will see that the LSTM becomes better. Now let's look at the GRU. So the GRU, with GRU, it's training a bit faster than the LSTM. It tends to be almost the same. Now let's go for really long sequences. Um, so we're using a sequence length of 120. Let's go for a sequence length of 240. I'm not going to do the feed forward anymore. So let's try 240. Not yet gotten to the point where we have vanishing gradients. That is where you will really see where the LSTM becomes better than the RNN. Okay. So RNN is taking longer now because the sequence length is much more. But you notice that feed-forward network actually trained fast because it is not reading the sequence in series, it's reading the sequence in parallel. And this is one of the advantages of using a transformer. Transformer also does similar to a feed-forward network in that it reads everything in parallel, so it trains faster. We're going to do that demo. But here, the RNN has to read the sequence um, um, sequential, right? And because it's reading it sequentially, right? Now LSTM, let's train LSTM on the same sequence. It's going to take much longer also. Yeah, it's going to take a bit of time. This is just epoch zero. So while this is going on, I'm going to show us another problem. So this time we're just dealing with sequences, right? And sequences that are basically, I should say, um, numeric numeric sequences. Now, we are going to also do something, but this time around, not with numeric sequences, but with sequence of words. Okay, so we are going to, I'll let this run, but we're going to do, I'm going to set up a new collab, and we're going to train a model to predict a simple LSTM model to predict words from a sequence of words, right? The next word from a sequence of words. Okay. Then I will then apply that to what we call a sentiment classifier. So, right. Okay. Yeah, this has gotten to this point. Let's plot the RNN versus the LSTM on a long sequence. Well, it does look like RNN still converges faster. So now with GRU, we train a GRU. GRU should be a bit faster to train than LSTM, but still a bit slower than the RNN. So again, I'll let this train while we Okay, sorry for the slight um, disruption. So I was saying that the reason why these three, when you look at the three of them, you'll be asking, okay, it seems they are basically the same, right? That is because the sequence length is still very small. So the three are more or less doing well, on this particular problem. By the time you increase the sequence length to much more, let's say 1,000, 2,000, you begin to see differences. But of course, that will take a bit longer to train, right? I might actually attempt that later on, maybe using a GPU, so that we can get it to train faster. So I'll do that maybe before the class ends, after we've done the other problem. But if you do use a GPU, you could try a much larger sequence length and see what happens. So here, this is now after training this model. I'm using the LSTM model. I can now do a prediction. So here it actually plots the original data and then the prediction. So you can see the prediction here, right, is not too far off from the original. I could also do it this way. Use I could use you know dots, and then I could use a color of red um here to plot this so that you'll be able to see, right? This is the actual data following roughly a sine wave, and then you see the prediction from the LSTM after training it that much. So it's a pretty good prediction, kind of. So that's kind of a summary of it. I'll come back to this again. I want to see which point the RNN breaks and LSTM becomes better, but it will have to be with really large sequence length, and I'll have to do that on the GPU. So what I want to now do is, I was saying we'll do prediction of the next word in a sequence, which we can easily do. So let's do that first of all. I'm going to so we'll do two problems. The first one is prediction of the next word in a sequence, and I'm going to do this really quick. In a sentence, right? So we have now moved from numbers to predicting numbers, numeric sequences, to natural language processing, which is, this is like the first steps. For natural language processing, though, there is a prior data processing step which you will have to do, right? And that prior data processing step is what we call an embedding. So remember, words you can only train models on numbers. Everything is represented as numbers. But for words to have meaning, right, semantic meaning, we use what we call embedding. So an embedding is essentially a vector that represents a word. And I can show you, and we'll talk about embeddings shortly. But I think we touched embeddings a little bit. Okay, I'm going to touch embeddings a bit more. Maybe when we go into a bit of natural language processing transformers next week. Okay. But an embedding is essentially a a long list of numbers, floating point numbers. But those numbers have meaning, right? We'll talk about embeddings when we meet next week, when we're talking about transformers and so on. But an embedding is a way of representing meaning. Think of it that way. It's a way of representing meaning, not the actual words themselves, not the letters of the words, but the meaning, right? So every word has a meaning, right? And the meanings are not always exactly the same, but there are small, slight nuances. So, um, prior to these days, we use language models, large language models to do embeddings, because the language models trained on data, language data, they have a much better understanding of meanings. So when you do embeddings from those, right, they make more sense. But prior to then, we were using pre-made databases of embeddings, which started off with human beings kind of creating them and then, you know, being trained with, um, less proficient models, earlier machine learning models and so on, right? So one of those embeddings is this glove, right? There are two sets of embeddings that you see used a lot. You have word2vec and glove, right? So word2vec is basically um, a function that you can use to generate vectors, right? So a word2vec, as the name implies, it means um, words to vectors, right? So let's see how we can use word2vec, right, to generate embeddings. That's the first step, right? So so in the in NLP, that's natural language processing, words have to be converted, to numeric representations that can be used to train neural networks, right? These representations are what we call embeddings, right? So one of the ways that you can generate um, is word2vec. So word2vec, there are two, right? You have word2vec, right? Word2vec. Word2vec is basically a very shallow neural network. All right. So it's a shallow neural network that learns vector representations. Okay. Right? Such that the words that appear in similar contexts will have similar vectors. That's word2vec, right? So, an example of it is this. If you have something like, if you have something like, let me just write this out. Okay, it's a shallow neural network that learns. Okay, so the way you use word2vec, it's because it's a new, you have to install it. Okay, and these are the dependencies that you have to install. Um, you have to install GenSim, right? NLTK, Natural Language Toolkits, right? And so you can get word2vec in there. Okay. Now, um, so there is, yeah. So the idea is this, right? Let me just put a diagram to help with the um so this is typically the idea in word2vec, right? The whole idea of embeddings is that if you have embeddings of words that have similar meaning, for example, king, right? And if you take king, you subtract man from it, right? And then add woman, you get queen. Because of the um because of the relationship between those words, the vector representations have relationships. And those relationships you can actually use some vector mathematics. We are going to talk about it more when we come back. So I'm not going to go into that now. But the vector mathematics really makes sense, and we are going to look at that. So words that have similar meanings will have vectors that point in similar directions in a multidimensional space, right? And words that have different meanings will point in opposite directions or close to almost opposite directions in a multidimensional space. So, all right. So this is how you use Word2Vec. You install the natural language toolkit and GenSim. Okay. Then let's do this. Import and the natural language toolkit. Then there is you can download, right? They have this punct. This punct is a tokenizer, right? A tokenizer is um an algorithm basically that splits words into tokens. So you can't just take the entire sentence and put it in an embedding model to embed it for you. You have to split the words into tokens, then you embed the tokens. And that's typically how it is done. So um typically, right, when you want to tokenize words, right? Let's have some examples. Um Yeah, so after downloading this, I think we need to also get the tokenizer. So after downloading this, you can get the tokenizer from nltk.tokenize, import word tokenize. So this is a word tokenizer. So let's take a few examples of some sentences. Okay, so these are sentences, right? You can then pass this um to a trade tokenizer. So let's try tokenizer a bit, right? So let's even just do tokenize, right? For my name is um John, right? Okay. Um okay, so first of all is I think it's having difficulty finding some characters. So um let's make it lowercase first so that I don't have problem. Okay, so I need to get punct tab as well. So I got punct NL. So let's get those. Okay. Um, all right. Let's try this again. Okay, so you can see the tokenizer has tokenized this, right? And basically it tokenizes it based on words. That's why it's a word tokenizer. Okay. So it breaks it down into words. So because tokenizers take individual sentences, right? So you can take this entire list of sentences and feed it into what tokenize, right? And you can get a list of tokenized sentences. So that's the first step. First step is tokenization. Then after you do tokenization, then you will do the embedding. Okay. So to tokenize, you can say tokenized sentences equals word tokenize. So we tokenize each sentence S, right? For S in sentences. So basically we will so basically you take each sentence in this list of sentences that we had created and you run it through the tokenizer. So you can now see we have a list of a list of lists, right? And each list contains a tokenized version of this, which is basically, since it's a word tokenizer, basically takes each word out and splits it up by the words, right? So you get the word tokenizer. So that's the first step, right? Then before you train, you now word to vec is a model. So you can then take that model, right, and pass it through word to vec, right? Um, so uh so here, so remember step one was prepare the tokenize the let me put this here. So first of all, yeah, you have a list of sentences you want to train. Um, Basically, let's just say training data. So this is the list of sentences, which is a training data. So that's the first one. Then you will now tokenize, right? Okay. Then um, you now train what to vec to generate embeddings, right? So what to vec needs to be trained a little bit or fine-tuned, right? So you train it on your tokenized sentences first. So the way to do this from GenSim. So remember GenSim, what to vec is in the GenSim. You import word to vec. So it's a shallow neural network that has been trained before. Okay. So now, by the way, there are many other ways you can do embeddings, but I always like to start this from here because this is like the beginning where it all started. Okay. Um, all right. So we now generate our word to vec model, or we create our word to vec model. You specify the sentences, you specify the vector size. So this vector size, you can choose whatever number of embedding dimension you want, right? It's always good. The bigger the dimension, the more, um, the better the embedding will be. But this dimension, right, is the is basically going to be the input size into your LSTM. So if it's too much, you also have slow training. Then the window is the context window size, right? When it's generating embeddings, it can actually go through the previous words. That's what context window basically means. The previous words, it looks at previous words, right? Um, Based on the size of the window to help it generate embeddings that are more contextually, correct. So that's the window 5. This is basically the context window, right? Okay, then mean count equals to 1. Basically, mean count is um, if words are not up to minimum count is 1. So words that are not up to 1 in number, it will ignore, right? Um, then workers. So workers is basically like the number of people that sorry, the number of workers, the number of code workers in the background I'll be doing this tokenization. I said people. Okay, so this is how you create a model, right? I pass in this. So SG, right, can be either 0 or 1, right? 0 means skip gram, or 1 means skip gram, and 0 means CBOW. We'll look at what those things mean later on. Okay, so with this, you create your model. Then um, So one thing with this context window is that if your context window is larger, the meaning is more semantic. Basically, it looks at more words around that word in order to do the embedding, right? But if the context window is smaller, it looks at less words around that word. So the meaning is more syntactic and less semantic. Okay. Right. So we create a model. So we basically create a word-to-vec model. Now we can use this word-to-vec model to generate embeddings. So the embeddings are always vectors. Like I said, a vector is basically a list of numbers. So I can, for example, do WV. Let's say a word like king. Okay. Remember, I'm embedding size. Um, I'm sorry. This is supposed to be um brackets. So for this word, okay, I have to use words that are in this list of sentences that have already been um, you know, tokenized. That's why we train the model on this, right? This word to vec train the models on that. So the reason why it's giving me this error is because I did not have king in my original list, right? So I can look for film, for example, film, and I'll get the embedding for it. Um, I can always print. So remember, it's a vector of length 100. It's a flat vector of length 100. You could also, and you can see it's just a list of numbers. So this is how you do embedding, and this is how you generate numbers that have meaning, that correspond to the meaning of words. You use the whole embedding approach. You could look at the shape of it, right? And you see that it's 100 because we specified that the vector size is 100. If we change it, it will give us. So with this now, we have embeddings. So the next thing you can do with embeddings is what we call similarity search, right? You can find words that are similar. You can find words that are similar. Um, so for example, if I want to do a similarity search with this word film, I can now do model dot wv word vec most similar, and I specify the word I will find that's most similar. So let's say king, for example. Okay, I still have to use words that are in my original vocabulary. So that's the thing with word to vec. There's something it calls a vocabulary, which is a total list of all the words that you gave to it when you were training it. You cannot ask for words outside of that vocabulary. So let's see, amazing. Right. So you now see that it gives you words that match this, right? And it's still going to come out from the vocabulary you have here. So when you want to train, you have to make sure you have a pretty large vocabulary. The entire data that you have, you can use that for a vocabulary. So you can see the similarity search is giving us the top score of 0.252 is absolutely, which is pretty close to amazing, right? And then all the other words. You can look for other words like, okay, let's say fantastic. I'm surprised fantastic is not here, but fantastic. And it was great, absolutely. So the highest score is it, which is interesting. So that's the other thing you see with what to vec. It is not really that intelligent, right? But you can use that to do your embeddings, which you can use to train a model. So that's the first way to create embeddings. Um, there's another approach, right? Um, which is using Glove. So Glove is a data set of embeddings, right? Which you can just use. Um, so typically how you use Glove is you would download, right? you would download the Glove embeddings. So you can get this from a bunch of places, right? So one place you can get Glove um, is Stanford has a place where it is. So this is where you can get it, right? NLP does stand for the Edu, right? There are a bunch of other places you can get it, and you just download this zip file. Okay, so let's do that. After you finish downloading it, then you can unzip it, right? And then you can open each. So if you look at our, let's see if it shows up here. Yeah, so you can see it's downloading already. It'll take a bit of time, so I'll let it finish downloading. After downloading, you can unzip it, and you have a bunch of text files which we will look at. Okay, so while this is downloading, if you want to continue after you have, so the Glove is pre-trained embedding, so the embeddings have already been done. So you just use those embeddings. You don't need to generate them or train a model on your um, vocabulary or your data set. The vocabulary is basically a data set of all the words that you use for whatever NLP task that you are doing. Okay. So while Glove is downloading, let me finish up with using the um, word to vec. Okay. Um, so um, so just showing you how to do that. Now, the next thing is you have to build what we call an embedding matrix, right? So an embedding matrix is a matrix that contains your words and the embeddings for them, right? So it's normally in the shape of the vocabulary size and the embedding dimension, right? So let me just put that here so you can see, right? That's typically the size, okay? So for this particular, the neural network, a matrix with the size, with the below shape, okay? So it needs a vocab size and embedding dimension. So how do you get your vocab size? Or you can, a simple way to do this, right, is um, this is a simple way to do this. So you are going to enumerate, um, remember when you trained your word to vec on your entire tokenized sentences, your entire tokenized sentences forms your vocabulary, basically. So word to vec, the vocabulary, the entire vocabulary of word to vec contains all your words. So basically your entire vocabulary. Okay. Now, um, you now run an enumeration on that. Okay. And you're now going to create this index, which is the word, right? And the position of the word. And we are starting from position 1, not from position 0. So that's what this does. Okay, if you now print word index, let me print it. You now see I probably should have, yeah, so you now see the word and its position. So basically, every word has a position in the entire word to vec. You can see that I have 20 words here actually. 1, 2, 3, 4. Even though my tokenization may show that it was more than 20. But remember, there are some words that may be repeated, right? So those words that are repeated are only counted once. For example, movie here and movie here, right? And a bunch of other words, in most sentences, if you are doing something that requires a longer vocabulary, you see that there are a lot of words that are repeated, like THEANDIS and all of those words. So, but this is a total size of my vocabulary that contains all of those words. Okay. So you do a word index and then you build the matrix. So, yes, so start first with the word index, then you build a matrix. The embedding matrix. All right, so we have a word index now. Okay, now to build the embedding matrix, we basically are going to run um, embedding through each of the words in that word index. So I think we already have NumPy imported somewhere, but let me just be sure. Okay. Yeah, let me import NumPy. Then we'll have the um, embedding dimension, right? Embedding dimension is essentially the vector size, right? Remember, the model is a word to vec model. So, and remember, we had said the vector size was what, 100. Okay, so vector size is 100. We had passed that in here, so it's 100. But we're just using that so that whatever it was, that's what we use. Then the vocabulary size is, right, the length of the word index, basically, which is the same thing as the length of the index to key. But let's just use word index in this case, plus 1. So the reason why we add an extra blank space for this, an extra slot, is for padding, what we call padding. So we reserve position 0 for that padding. That's why we didn't start from 0 here. We started from I plus 1. So we started from 1. Okay. Right. So now the vocabulary, the embedding matrix is going to be, remember the dimension of this vocabulary size and embedding dimension. We've gotten the embedding dimension, which is 100 in this case. That is the size of the vector, embedding vector. Then the vocabulary size, which is the number of words in your vocabulary, which in this case, if of course you look at it, we had 20 plus 1. The 1 is a 0 padding, right? So that's the total dimension. So we'll start by creating a matrix of zeros, right? Of that shape, right? Matrix of zeros, the vocabulary size, right? And embedding dimension. Then in this matrix of zeros, we begin to populate the actual embedding in there. And that is what this loop does, right? For word I in word index. So remember, we have word index, which is basically a dictionary of the word and the index location. So the word index of items will give you that as word and index location. So in the embedding matrix I, right, we will now generate the embedding for that word. So we'll now end up having embedding matrix being the vocabulary, that is the number of words in the vocabulary, and then that's the rows, the height, or the number of the the y dimension, and then the x dimension is the number of features, which is basically the size. So if we look at this now, we can then print out that embedding matrix, and you see what it looks like. So the first row is still zeros. We are not using it for anything. The zeroth row, if you may call it so. Then the row one contains the embedding, the 100 size vector embedding for the word that is at position one, and the word at position one is movie. So if you go look at movie, I don't think I remember doing that, but I did film, and we saw the embedding. So each of this row is the 100 number, the 100 vector size embedding for the word in that position. And that's what the embedding matrix means, right? So you just start with this embedding matrix, you create it. Then you can now create an embedding layer with PyTorch, right? So that will be the next thing. Create a PyTorch um, embedding layer from the um, embedding matrix. Okay. So the simple way to do this is, um, of course, we have to import torch, import torch dot neural network as NN. Then we now create our embedding layer. Embedding layer equals NN dot embedding, right? Dot from pre-trained. So pre-trained means I already have embedding vectors in place. So I don't need to train this layer to be an embedding layer. I just pull the embedding vectors, right, from another one that's been trained. So remember, Word2Vec is a shallow neural network that generates these vectors. So it's kind of already trained or pre-trained. So use from pre-trained, right, to get that. Yes, you convert the embedding matrix into a touch tensor. In this case, a touch float tensor, right? The other way you could have done it is touch.tensor, and then you change it to float, right? So, make it float. Then you specify the padding index. So in this case, remember we said that we'll start with a padding of 0. So we specify a padding index of 0. Then freeze equals true. Freeze equals true means that I don't want to train these weights or fine-tune training on these weights, right? These weights should not be trained. That's what freeze means. When you freeze a layer, it means that when you're doing back propagation to train the entire network, right, this particular layer will not, its parameters will not be updated. So this is something we normally use in what we call transfer learning or in pre-trained fine-tuning. Like, if you want to train, if you want to improve a model that's been trained and some layers, you don't want to mess around with those layers, right? So you freeze those layers. So that's what this means. But you could also decide to do freeze is false, right? False means you don't freeze. So this particular layer can still be fine-tuned. It can still be trained, improved as part of the thing. So now the question is, when do you decide to use freeze and when do you decide not to use freeze, right? You use freeze. Freeze is recommended for tasks when you don't want the embedding to change. So for example, if you are doing sentiment analysis or sentiment classification, right? Okay. Um, so you may say false to allow the model to learn, right? Um, if you don't want to. So for sentiments, if anything where you want the context of the embedding, right, or you want the embedding layer to adjust to the context, right, you put phrases false. But sometimes in cases where you don't want the embedding to change, you are sure of the embeddings, right, you can say phrase is true, right? So well, let's leave it at false, okay? So now if I want to train, so this is I now have all of this, right? I have all of this. Um, so I want to now create a simple LSTM that can predict words. Okay. So now let's create the LSTM. Okay. So what we'll first of all do is we have we have our embedding matrix. So we will just create next word. Let's call it next word predictor. Okay. So again, we take from nm.module. We'll define our init, and then we'll pass in the embedding matrix, right, as a parameter that contains those words. So yeah. So now um, you can specify the number of embeddings and the embedding dimension. We need this information. So we just get it by destructuring it from the embedding matrix shape. Okay. This will help us to because now you need to create an embedding layer, and that's what we are doing here basically. We create an embedding layer, and so you see when I created it here as an example, this was just basically an example, right, to show you how to do that. But this embedding layer, you actually put it inside your text. So remember, the embedding layer is the layer that would translate the words in text, right? That will translate the words in text into um the numbers, right? So we still yeah, we still do this touch.tensor embedding matrix dot float. Okay. And it should be, let's see, right? So I didn't bother to specify padding index or specify freeze, right? Okay, so the embedding vector is the first, sorry, the embedding layer is the first layer whenever you're doing natural language processing. You need to convert words to vectors. That's what the embedding layer does. So then we now create the LSTM. So the LSTM is going to get its input from the embedding layer. Okay, so the input size needs to match the embedding dimension. So remember, your embedding matrix has the number of embeddings, which is the vocabulary size, and the embedding dimension, which is the size of the embedding vectors. So that size of the embedding vector, embedding vector essentially becomes the number of features, right? The features that are passed into the LSTM. So it has to match the input size of the LSTM. Then you can decide a number of hidden size. So in this case, let's just say 128, pretty large. Batch first is still true. Okay. And then we now from the LSTM output, we will now pass it into another fully connected linear layer. Now, because we are doing a next word predictor, right? The output has to match the embedding size as well, because I want to predict which word. So the output has to match not the number of embeddings, but the embedding dimension. So I'm effectively saying um, predict an embedding. Then we would take this embedding and convert it, right, back into um you convert it back into the corresponding words, which Okay. All right. Oh, okay. Um, yeah, this is correct. When you are doing a next word predictor, the output actually has to match the vocabulary. Yes. Because what you want to do is you're not actually trying to generate the embedding to match what the next word that is predicted. Rather, you are trying to generate the probability that the next word is um, the particular index. Okay. All right. So I think, yes, yeah, I think I missed that. So maybe the other, let me rename this to vocabulary size so that we can know. So we have the vocabulary size. So this is still a predictor, right? Um, but what we are saying is this: what is the probability that the next word? Remember, the vocabulary size is well, it should actually be since we have padding in this, right? We have padding. Um, so it should be vocabulary size plus one. Yeah. Okay. So since we have padding from what I did before, I have to include the padding index. So the padding index is zero. And okay, freeze is false. Yes, freeze is false. In this case, yeah. So okay. So after that, so the next thing is you define your this is going to be basically a probability. So it's probability logits. You know what we mean by logits, right? Logits is numbers that represent a probability distribution. So typically we are going to do something with it later on. But for now, we can now define our forward, right? And yeah, you pass X through the embedding. Then when you pass X through the embedding, you now run the LSTM output, right? So you have output. Um, remember, LSTM gives you the output, gives you the hidden, and it gives you the cell state, right? It gives you three things, right? Okay. So um, then you can now take the last time step. Okay. You take the last out step. That's what this does. This output minus one. This because the way the output is, remember when I showed okay, it wasn't on this screen, but on this screen where I showed how the shape of the output looks like. The output is always going to be batch size, sequence length, and hidden size. Okay. Batch size, sequence length, and hidden size. So um we have outputs here. We have so you take the entire batch. This is you take the last in the sequence. So this is what you're basically taking is that the last item in the sequence, right? But you take the full vector dimension. So that's what this does. and you pass that into your fully connected layer. Remember, the fully connected layer is the same as a linear size, and then the output should be the vocabulary size. So you do that and you get the output. That's basically what this does. Okay, and you return that. So this output is the logits, what they call logits, which is basically the probability distribution. So what's a probability distribution? Let me just see if I can explain that. So remember, we started off by saying these are word indexes. So these word indexes translate to a list of words. Now, what this is going to likely predict is something like this. Let me just give you an example of what it will predict. It will predict something like index one, the probability is, in fact, let me put it the way it's likely going to come up. It's going to be a torch list. Index one can give you something like 0.00123, right? Index two will be 0.21. Just random numbers. In fact, let me simulate it by doing this, right? Let me simulate it by doing this so you can see what the probability distribution is. It is going to be something like torch dot um, random, right? And the shape will basically be the vocabulary length. So in this case, the vocabulary length is 20. But let me just say length of word what was this? Okay, we have it as vocab size already. So yeah, vocab size. And then the embedding size, right? Which in this case, let me just put 100. So that's the logic. This is what is coming out from that. It's basically going to be um um so run like let's do this. Let me use np dot random. Okay. Um dot So effectively, you're getting a list of random numbers that is the same size, then reshape into vocab size and 100. So this is this is what Logits looks like. Okay. Yeah. So yeah, effectively saying this is not correct. It is just vocab size. I'm sorry. So basically, we don't even need a reshape. Think about it this way. It's basically a list of numbers, right? It's a list of numbers that represent the probability that, so this first position, it would be like saying that the probability of the first word, the probability of the next word being movie is 0.813 because this matches the index of movie. The probability of the next word being ever, which is index position 2, is 0.0018. So that's what a probability distribution is. It basically means that we have 20 words here, right? And we have 20 numbers here, right? And what we are saying is that the probability that any word, the next word that comes out will be any of these corresponds to this probability number here, right? Typically, of course, you ask yourself, probability should sum up to 1, right? But we are talking neural networks. So these logics may not necessarily sum up to 1, right? It is what it has been trained on. So you can use a softmax to basically normalize this so that the sum of these probabilities will always be 1, which is typically why when you are training um, a probability matrix like this, you will use softmaxed layer, right? As the last layer that comes out if you are training on stuff like that.